Thank you, Leslie and Valerio, for this kind invitation to talk. I have to confess, you know, when somebody asks you to talk about the history, there's a temptation to become rather self-indulgent, and I apologize if at times I become rather self-indulgent talking about, you know, my own life and background. But I wanted to focus on, an area which I guess I've devoted quite a large part of my life to, which is the development of ensemble prediction systems. And of course, these, you know, now span the whole of weather and climate science, but I'm going to focus in this talk primarily on, if you like, weather to seasonal timescales, the sort of initial value type of problems. So the left-hand side of this slide is an example of some what we call stamp maps from an ensemble, from the ECMWF ensemble system. And the right-hand side is something I'm going to hopefully at the end get to talk about, which is the application of these ideas in helping to prevent disasters. So this was a disaster which happened after Typhoon Haiyan hit parts of the Philippine Islands. And aid didn't really start reaching these islands till many days, in fact weeks, after the event hit. And the question is, can we make better informed, proactive decisions, providing aid before the event hits, using ensemble systems? Oops, let's go down. Okay, sorry. There's lots of people I need to give thanks to here, and it would just take me too long to go through everyone's names. So I'm just going to sort of acknowledge that the work I'm going to talk about is really the work of a lot of people, and quite a big effort over the years. Yeah, so just to start with a bit of, if you like, self-indulgent history. As Leslie said, my original PhD was actually in theoretical physics, in black hole physics and stuff like that, which was quite exciting at the time. It was the era when Stephen Hawking had just announced that black holes evaporate quantum mechanically, and that got people extremely excited about things like quantum gravity and so on. And I came to the end of my PhD, and I actually had an opportunity to work with Stephen on some of these things, which certainly my parents were very keen that I should accept. But I came to the conclusion after a lot of thought that I wanted to spend my life doing something actually a little bit more useful and looking at rather esoteric problems in black hole physics. And by complete coincidence, I met somebody who was a meteorologist who convinced me that the sort of mathematics I knew would be relevant. And so I applied and was successful in joining the UK Met Office, completely retrained. Perhaps I should say that one thing I think I sort of took with me from my early PhD days was a deep appreciation of some of the beauty and subtlety of nonlinear processes. General relativity is, of course, a very nonlinear theory, but it's extremely beautiful for that. And I've never felt that nonlinearity was something that should be shunned or should be kind of swept under the carpet. Because often some of the deepest insights come when one takes, sort of acknowledges nonlinearity and looks at it, you know, not just as a second order term in an expansion in some parameter, but as a fully fledged, you know, process in its own right. And in fact, my first work at the Met Office was in the dynamics of the stratosphere, things like stratospheric sudden warmings. And with a colleague from Cambridge, Michael McIntyre, we discovered the existence of breaking Rossby waves in the stratosphere. The big planetary waves that propagate up there become so large amplitude they basically start to break. And it turns out this wave breaking is crucially important to understand the dynamics of stratospheric sudden warmings. And the absence of wave breaking in the southern hemisphere is crucially important for understanding why the ozone hole first appeared in the southern hemisphere. So anyway, so this was just an example of nonlinear process wave breaking, which which I guess I worked on because of my sort of deep interest in nonlinear processes. And the Met Office is a kind of a slightly quirky, at least in those days, it was a quirky system in that the paper with McIntyre got published in Nature. We had a front cover of Nature. It was all very high profile and very successful. So I got promoted to be a group leader in the Met Office. But in those days, you could only, you had to go to a group that had for where there was a vacancy as a group leader. And there was actually only two choices. One was the training college, and one was a branch called synoptic climatology. And I have to confess, I had no idea whatsoever what synoptic climatology meant. It just sounded like two strange words. But I really didn't want to be going to the training college. So I just said yes to that in the hope that that was going to be a good decision. And it turned out in synoptic climatology, they were, the main objective of the branch was to develop monthly forecasts, so long-range forecasts. And these were done entirely by statistical empirical models. There was no dynamical modeling at all. It was done essentially using predictors, sea surface temperature predictors, and these were fed into a statistical empirical model. And the output of the models, the statistical models, were probabilities of a kind of a forerunner of weather, what we would now call weather regimes. So these were actually called Lamb weather types after Hubert Lamb, who was a scientist at that particular branch many years before me, who then went on to found the climatic research unit at the University of East Anglia. Anyway, so that was the branch I was sort of, I was sent to, and numerical models were becoming, they were already established in short-range weather forecasting, and they were already starting to be used for climate work. So in the 1970s, Manabe, for example, in the States, had started to use GCMs to look at climate change, and this was also being done mainly by John Mitchell at the Met Office. But this sort of area of monthly forecasting hadn't yet been studied at all with numerical models. So I thought, well, this would be a good topic to get into, and used one of the climate models actually of the Met Office, the one that was used for climate change, to do monthly forecasts. But the question was immediately, how do you blend a dynamical model output with one of these statistical empirical models? So the idea was not to replace the statistical empirical models, but to somehow supplement them. And it became obvious really right from the start that we would have to do some kind of ensemble. Now I should perhaps just I've got some names up at the top, which were people that certainly influenced me in those early days. Now, Ed Lorenz, we're talking about now the early 1980s. People were, of course, aware of Ed Lorenz's work, the limited predictability of weather, and the notion that if you were doing long-range forecasting, it would have to be something probabilistic. Epstein had written a paper trying to outline a kind of an approach to probabilistic modeling based on things like the Liouville and Fokker-Planck equations. But these were almost impossible to actually solve in practice. And I think it was Chuck Leith who first suggested that some kind of Monte Carlo method might be a better way of developing probabilistic types of prediction. And Kiku Miyakoda at GFDL and Jagadish Shukla, who was then originally at NASA, who then moved to form his own group, COLA. They had all been promoting these ideas about essentially ensemble forecasting for monthly prediction. So with James Murphy, we put together a rather simple ensemble system where essentially the initial conditions were just lagged by, I forget, it was 6 or 12 hours. I think it was 12 hours apart. What do you call now a time-lagged ensemble. But this actually went into the operational, in 1986, the operational monthly forecast system of the Met Office. And we used the ensemble to produce probabilities of these weather regimes. so that in a sense was I think the first use of ensemble forecasting in an operational context. And I just want to make this point because it's going to contrast with what I'm about to say in a few minutes, that this was not considered to be especially controversial, or, I mean, I suppose it was somewhat innovative, but nobody kind of questioned it or said, oh, this is not a good idea. It was widely received and supported. So when we come to, well, I have to say I joined ECMWF in 1986, and as I'll talk about, with a view to trying to introduce these methods into medium range forecasting. But here this is where I started to encounter kind of resistance to this idea. And I think one has to, if you go back to the 1980s, there was a kind of a very strong divide. And I wouldn't say actually it's completely dissipated today, but it's much less strong than it was in those days. And curiously, two people, both from the same department at MIT, were kind of spearheading these different, if you like, concepts. So Charney, who of course was headed the original team founded by von Neumann back in the 1940s to use computer models to do weather forecasting. You know, they had basically developed this notion of deterministic prediction. And in the 1960s, people started to ask the question, how far ahead could you forecast using a deterministic model? And indeed, ECMWF was set up on the whole kind of basis that there was this concept of a limit of deterministic predictability of, let's say, around 2 weeks or so, within which, you know, the concept was you could predict the weather in a deterministic way. And then it was accepted that beyond that limit of deterministic predictability, if you wanted to, you know, examine how sea surface temperatures might influence the weather, you're necessarily talking about probabilistic and using some combination of statistical empirical models and numerical models. So I can't sort of emphasize in a way how strongly that divide, you know, that very almost like a brick wall, if you like, between these timescales existed in those days. I guess I formed very quickly the view that that concept was deeply flawed, and I think this type of figure, and probably I have to thank Michael Gill for sort of getting me to think about this problem in a sort of nonlinear deterministic dynamical system way. But this figure from the Lorentz model points that out extremely clearly, that in a nonlinear system, the predictability of that system over finite times can and indeed will vary very substantially with the initial condition. And that's actually a direct consequence of nonlinearity. So the equation I got at the bottom here, the dx by dt equals f of x is a nonlinear equation. You linearize it to look at how small perturbations will grow. And the operator on the right-hand side is a functional derivative of f with respect to x. So if f is nonlinear, so it's quadratic, let's say, or more than quadratic, then df by dx will be at least linear and hence depend on the state itself. So the growth of small perturbations will depend on where you are on the attractor. And that's extremely clear in this diagram here, that the bottom one is extremely unpredictable. So you might be doing predictions which on average are inside this limit of predictability, but there are going to be occasions where the predictability is extremely short and you lose skill very quickly. And this was sort of the argument I was trying to sell, that that to be able to quantify that ahead of time, we needed to develop ensemble prediction systems for the medium range as well. But you know, if the technique was just a matter of doing some, you know, small bolt-on calculation at the end of the deterministic forecast, nobody would have had a problem. But the fact that this meant taking very significant amounts of computer time, you know, to run a model, you know, 50 times, let's say, that met with a lot of resistance, because the argument was that we should be using that computer time to improve our deterministic models, increase the resolution, improve data assimilation techniques, and so on. And as I'll just say at the end, I'm the most enthusiastic of people about developing high resolution models, but doing them in a completely deterministic way is, in my view, totally unscientific. But anyway, so that was the situation, let's say, in the mid-80s. But fortunately, nature played me a very good hand of cards, in the sense that in October 1987, I think the worst storm that, people reckon the worst storm that hit southern England in about 300 years occurred. But not only that, the weather forecaster, this famous guy now, who's become, his name in the English language has become eponymous with, or synonymous, let's say, with a failed forecast. The poor chap Michael Fish, although I don't feel so bad about him, because he's made quite a good after-dinner speech, living from after-dinner speeches, talking about weather forecasting and so on. But so he's become well known, but his name, the governor of the Bank of England, for example, or his chief economist, described the failure of the bank to predict the financial crash of 2008 as their Michael Fish moment. So it's become part of the English language now. But anyway, it wasn't his fault. He got the computer forecast from the Met Office in the evening of, I think it was the 14th or 15th of October, I forget the exact day now, 15th, I think. And it didn't have any particular warning of a severe storm. So his forecast for the next day was of a somewhat breezy, but nothing exceptional sort of a day. And then in the morning, after the most unbelievable devastation that occurred in the early hours of the morning, the town of Sevenoaks in Kent famously became No Oaks. But worse than that, of course, people lost their lives, and all sorts of damage was done to buildings and cars, and upturned aircraft, and boats had been ripped out of their moorings, and all sorts of stuff. And the BBC anchorman basically said, "You chaps are a fat lot of good last night. If you can't forecast the worst storms for several centuries, 3 hours before they happen, what are you doing?" And this led to a big inquiry of the Met Office. The people were calling for the Met Office director to resign, all sorts of things. For me, I was in a way delighted. Maybe I shouldn't say this, but in a way I was quite happy that this happened, because it was a really good example of where this reliance on deterministic prediction was letting us down. And in fact, retrospectively, with colleagues at ECMWF, we ran the October 87 case, and the top here are the stamp maps 2.5 days before the event. And you can just see by looking at my eye the surface pressure. There's a phenomenal dispersion of solutions, much more than you. Typically, if you looked at 2 days or 3 days, all the stamp maps look by eye on this sort of scale, this sort of synoptic scale. They all look pretty much identical. But in this case, the divergence was just spectacular. And then you can say, well, what would you do with that information? And this is actually where I kind of depart from Chuck Leith's paper. I mentioned Chuck Leith earlier, and certainly his ideas about Monte Carlo forecasting were important. But he very much took the view that the main purpose of a Monte Carlo forecast is to produce an expectation value, to take the average of all the forecasts. And in my view, that's pretty much the worst thing you could do, because if you averaged all those 50 maps together, you just get some very bland looking, unexceptional weather event. And this, incidentally, is why in Leith's paper, he suggests that maybe you don't need more than about 9 or 10 ensemble members. But if you really want to forecast probabilities, you need more than that. And at ECMWF, we've stuck at 50 for many years now, which I think is probably a minimum number. Anyway, so if you analyze the forecast, not in terms of some averaged quantity, but in terms of a probability, and here, this is at the lower diagram, probability of hurricane force winds, you get probabilities of 30 or 40%, which I think, for somebody who has a boat moored on the south coast, or has a light aircraft parked in an airfield in southern England, or indeed if you just bought a Lamborghini and it was parked underneath a big oak tree outside your house, I mean, these are all things where a 40% probability might be high enough for you to warrant taking precautionary action ahead of the event. But in any case, this demonstrated very, very clearly, I think, that one cannot rely on deterministic prediction methods, and that one has to acknowledge the fact that sometimes, because of the non-linearity, again, it comes down to non-linearity of the climate system, the predictability of the weather and climate can vary, and it can be intermittently very, very short indeed. I just thought I'd talk very briefly about, well, let me just say, so I think this event helped to overcome a lot of the resistance, and in 1992, I think it was the first operational system, the system went operational, and NCEP did something similar around this at the same time. And I think I was hearing that Yehenia Kalny will speak in this series later on, so she'll give her perspective on the same issue. But there was a practical problem before we could get to, and I just thought I'd spend a few minutes on this, kind of interesting from a dynamical point of view, I think. How do you actually create perturbations? You know, in some sense, you say, well, you just add random perturbations to the analysis. But there's a problem in a way. Sorry, just can you hold on 1 second? Okay, sorry about that. Because if you just add if you add perturbations that are too large or too either in scale or amplitude, then they're obviously unrealistic. They're not representative of initial condition errors. The problem is if you make them small in scale and small in amplitude, they tend to get damped by numerical diffusion. So rather than having a butterfly effect, you find that the perturbations don't do anything, and you seem to have much higher predictability than you actually have in reality. And in addition to that, just adding random noise in different variables will typically lead to very unbalanced perturbations. And again, the model's numerics will just damp those out very, very quickly. Now, the technique we had used to look at the technique we used at the Met Office of using consecutive 6-hour analyses was just not really a useful technique for these medium range forecasts, because you know you'll end up using analyses which, you know, 1 day into the future might be, I don't know, 4 or 5 days old. So this is not a good technique. And I actually pondered this for quite a while after I joined ECMWF, before we sort of had a working system. And in pondering it, I started to do some slightly kind of related but tangential work, which actually turned out to be important. So let me just talk about that briefly. I mean, one of the questions which was one could look at just by going back to the archives was what types of flows tended to be were associated either with low forecast errors or high forecast errors, just deterministic errors. And it turned out that the Pacific North American teleconnection pattern did discriminate between high and low forecast error forecasts, and this is a pattern which came out of a regression analysis. And I used a barotropic vorticity equation model to look at how small perturbations would grow with these different basic states, which either had the PNA pattern added to it or taken away from it. And you can see the growth of initial perturbations at day 2, 4, 9, and 30. The top row is with a positive PNA state that was associated with states where the medium range forecast was relatively skillful. And the bottom was with a basic state with the negative PNA, where the forecasts were relatively unskillful. And you can see that you know, clearly the bottom basic state is more barotropically unstable over this 30-day timescale compared to the top one. So that was all very nice and fitted in very well with this regression analysis. But when I started to analyze this further, it was I was kind of really surprised, and I was convinced for a long time I had a bug in the program, that if you do a normal mode analysis, this upper state was actually was actually, sorry, less stable. Yes, so the X, if you look at the growth rates of the fastest growing normal mode, so the eigenvalues of the largest eigenvector, then the growth rates were actually larger in the upper row than the lower row, which is completely contrary to what it looks like here. And it took me quite a long time to realize what was going on. And I have to say, in this respect, I was enormously influenced by work that Brian Farrell from Harvard had been doing. He was been studying things like Charney and Edey baroclinic instability problems, and making the point that in reality, these baroclinic waves are not growing with the normal mode growth rates, but something which he would call optimal growth rates. And this is to do with the fact that the eigenvectors of these basic state flows are not actually normal. So this is a schematic diagram of what's going on. You have psi1 and psi2 are two so-called normal modes, but they're eigenvectors, but they're not normal in the sense that they're not orthogonal to each other. And they're not orthogonal to each other because the differential equation that one is, the linear equation one is the linear differential equation one is solving, is not a kind of a self-adjoint differential equation, or the operator is not self-adjoint. The equation is not what's called a Sturm-Liouville equation. But what this means in practice is that you can see this, I think, in a sort of a graphical way. If you take say two eigenvectors like psi1 and psi2 that are not orthogonal to each other, and you construct a perturbation nu naught, which is the difference between psi1 multiplied by a big number minus psi2 multiplied by a big scalar number, such that the difference has unit amplitude. So nu naught on the left-hand side there has unit amplitude. Now let's imagine both of these are actually decaying in time. So these vectors, the A1 vector decays in time. So the tip of the arrow decays. The tail of the arrow also decays, but in this case, I'm assuming the tail is decaying faster. So both of these eigenvectors actually have decaying, they have negative eigenvalues, if you like. But if you look at the difference, you can see that at least for a finite period of time, the difference is actually growing. And the thing that determines this growth is not the eigenvalue, but this parameter theta, which essentially measures how, measures this non-orthogonality. Basically what this eta is the adjoint mode to psi1, and the adjoint of eta1, if it's just a two eigenvector system, then eta1 will be orthogonal to psi2. So theta is basically measuring the angle between psi1 and eta1. If you have a self-adjoint system, then psi1 will point along eta1, theta will be 0, and this gamma parameter will be equal to 1. But when theta becomes non-zero, then this dips below 1, and you start getting values greater than 1. And the closer theta is to 90 degrees, the closer gamma is to infinity. And it's essentially this gamma factor that is determining, that's determining this growth rate. You can formulate this in a slightly different way using what are called singular vectors, and this has become an extremely important part of the ensemble system. These singular vectors, one thing, sorry, just go back to here again. If you look at these perturbations, they're changing direction in state space. So it means the perturbations are not modal. They don't have the same shape as time evolves. And you can see that in this calculation, which I did with Roberto Buizza of these singular vectors, that they start off at relatively high wave numbers, and then they grow to synoptic wave numbers. This is wave number versus energy or something like that. So these actually have exactly the properties one wants for a perturbation which might describe analysis error. They're initially at relatively high wave numbers. They're meteorologically balanced, so that's a key point. The calculation is done in a way which they're integrated over sort of a 2-day period. So they have the right, if you like, balance type of constraints in them, and they grow to synoptic scales. So we did an awful lot of work at ECMWF looking at these singular vectors, and they really became the basis of the perturbations that we use in the Ensemble forecast system. And indeed, to the present day, that's still the case. I thought I'd just briefly talk about the second part of the Ensemble system, which is the stochastic physics, because it's not only the initial conditions that, or the observations, if you like, the initial conditions which are uncertain, the model itself is uncertain. And of course, in the uncertainty comes because we have to truncate the equations. We have to truncate the Navier-Stokes equations, for example. And we represent, as you all know, the unresolved part by these heuristic formulae. We call them parametrizations, makes it sound a bit more fancy than heuristic formulae, but that's basically what they are, heuristic formulae that are very approximate and uncertain. And by the way, these are not cheap either. They take up quite a significant part of the computing time. And so, you know, we can resolve baroclinic waves, but we can't resolve convective instabilities, or we can't resolve Gulf Stream mesoscale eddies, things like that. So the things below the line have to be parametrized. So I missed that. The problem with convective, well, the problem with parametrization in general is that it's based on a kind of a statistical mechanics view of the world, where you have processes which are occurring on scales much smaller than your grid box scale. And so you try to represent all of the processes in a bulk formula way. So the parametrization is essentially a bulk formula for the process that you're trying to parametrize. And if the world was like this, then of course everything would be fine and dandy. But the world is not like this. It has these multiple scales. You have small convective scales, you have medium ones, you have very highly organized mesoscale convective complexes. And that scale structure is consistent with one of the symmetries in the Navier-Stokes equations, the so-called scaling symmetries. And that's consistent observationally with the power law spectrum for atmospheric motions. And it's really this, the truncation of the equations basically violates this scaling symmetry. And that's what's introducing the errors and the uncertainties into the model. So one way to do slightly less damage to these scaling symmetries is to make the parametrization stochastic. And this is something with Martin Miller and Roberto Buizzo, we developed a scheme where basically the parametrizations are now represented in a sort of stochastic way, where R is now a stochastic variable. And it's done in this kind of multiplicative way. So in regions where the parametrization tendencies are strongest, say over the tropical West Pacific, then the stochasticity tends to be largest. And in regions of the atmosphere where the parametrizations are very weak or unimportant, then the stochasticity is very small. But basically we have this additional stochasticity. And so by running ensemble members with different realizations of the stochastic variable, then we get this additional source of uncertainty into the ensemble. I thought I would just very briefly run through a couple of interesting examples of the benefits of stochastic parametrization. I mean, the original motivation was to improve the probabilistic skill of the model, and it was particularly noticeable in the tropics that the skill scores where you just perturbed initial conditions only were not very good, because too often the verification lay outside the ensemble. What this diagram shows is are some sort of probabilistic skill scores. I won't go into this sort of continuous rank probability skill score for rainfall. I think it's rainfall. Oh no, it's actually 850 temperature. It's the 850 hectopascal temperature in the tropics anyway. So this would be the original deterministic model, skill dropping off very quickly. And this is the ensemble with, sorry, sorry, get this right. This is actually an ensemble as well, but it's without any stochastic parametrization. And these are all ensembles with different flavors of stochastic parametrization. But you can see, doesn't really matter what type of exactly the precise flavor you use, but there's a big difference in skill between the ensemble without stochastic parametrization and with. Now, in more recent years, people have been looking at whether stochastic parametrization actually has an impact on the climatology of the model. And a former student of mine, Hannah Christensen, who did this work when she was a postdoc at NCAR, showed, for example, that if you take the NCAR, this is a version of the NCAR climate model, and in this particular figure, we're looking at El Nino, ENSO, and this, she's showing like a power spectrum of ENSO variability in this NCAR coupled model. And basically, this model has much too much power at, I don't know what it is, at timescales of a couple of years or so compared to the observation. So, and this is a very common error. You can see this in a lot of the CMET models. They have very periodic or quasi-periodic ENSOs. Now, putting the stochastic physics in pretty much completely cured this problem. Now, you may say, oh, well, you've just put noise in, but remember the noise, and I haven't really spoken about this, but the noise only has timescales of a few hours, spatio autocorrelation timescales of a few hours. So, again, something quite profoundly nonlinear is happening in this noise getting up to damp timescales of years. So it's an interesting result. And this is something that we're particularly interested in at the moment. This is actually work that I was originally alerted to, done by Frank Kwasniok from Exeter. If you take just something like a Lorentz 63 model and add stochastic noise to the variables, then you find that the regime persistence timescale is increasing. I think you can see that by eye. And we found very similar thing with the Charney-Devore model, that the persistence timescale increases if you add stochastic noise. Now, this is a real problem with current generation climate models. They tend to be very under-persistent in terms of weather regimes, things like blocking. And we're looking quite closely at this phenomenon in the context of climate models to see whether noise will actually help alleviate some of these persistence problems. I could speak a bit about this. We have an understanding of why this is happening in a dynamical systems framework, but it's less clear whether that's happening in the full GCM or not. Okay, well, there is a zillion ways of verifying ensemble forecasts. One of my favorite ones is actually this type of diagnostic, which is called potential economic value, that originally came out of work by Alan Murphy back in the 1970s and 80s. And this is comparing an ensemble forecast system in blue with a high resolution deterministic system in red. And the idea here is the x-axis is labeling different users who have different cost-loss ratios. The idea is that they are vulnerable to, let's call it a weather event E, in the sense that if the weather event occurs, they will incur some loss L. but they can take protective action against that loss at cost C. I mean, one assumes that the cost of taking protective action is less than the loss. So if it's zero, the cost is trivial, and therefore you should always take protective action. If the cost is equal to 1 compared to the loss, then it sort of makes no difference whether you take protective action or not. But in between here, then in principle, you can get value from the forecast in deciding when to take protective action. If you have a just a deterministic forecast, then the only decision that you can make is to say, I will take protective action when the deterministic forecast predicts the event. But if you have an ensemble, you have a much more nuanced decision process, which is to say, I will take action when the probability of the event exceeds this cost-loss ratio. And basically, these two curves compare the values of the two forecast systems using these different decision thresholds. And you can see that not only does the ensemble, despite the fact it has lower resolution than the high resolution model, it has higher value, but also the value extends over a much larger range of users. Okay, so that's pretty much a kind of a quick sort of summary of how I kind of got involved in all this stuff. And as I say, I haven't talked very much about climate things, but focus on ECMWF. I wrote all this up in a paper in the QJ a couple of years ago. So if you are interested, you can read some more in that paper. I just thought I'd take the last 5 minutes or so in just because I just thought I should try and look forward as well as looking backwards. And a few weeks ago, I published, it's more of a kind of an essay than a paper on the archive, kind of tried to talk about the future of NWP and what NWP should, in my view, look like in 10 years from now. And one of the reasons why I kind of wrote this was because I do feel that advanced early warning systems is an important part of trying to make society more resilient to the extremes of weather that we're going to see more increasingly and more vigorously with climate change. And this study by the Global Commission for Adaptation looks at all the sort of different types of actions that can be taken to make society more resilient, protecting mangroves, for example, or improving agriculture and so on. But in terms of this particular metric, which is benefit cost ratio, strengthening early warning systems were deemed to have the greatest benefit cost ratio. So for every dollar you invest, this would have the greatest payback. So I think it is important that we think about how to improve our prediction systems looking forward into the future. And one of the things which I'm enormously encouraged about is which relates to this very first slide, about trying to be more proactive ahead of extreme weather events. And the Red Cross, Red Crescent aid organization has been developing what they call forecast-based financing systems. So providing financial aid to regions which are predicted to be affected by some sort of severe event. It could be a storm, or it could be a drought, or flooding event, or whatever. But for this to make, for this to be a viable type of a system, they need to make sure the forecasts are reliable. And what that means in practice is that they would take decisions to release these types of financing systems when a trigger which is based on a probability. So it could be like 80% chance of some exceptional storm or something, or whatever the trigger is for a regionally specific extreme event. Yeah, I mean, these are some examples of, this is actually a nice example of 3 hurricanes or tropical cyclones, which have different levels of predictability, a bit like the Lorentz model. So, a week before, it was pretty clear that some kind of cyclone was going to hit Bangladesh. And so probably this would be a big enough probability to trigger could be big enough probability to trigger forecast-based finance in this situation. This is Katrina. I mean, not that one would be providing aid to the United States, but this is Katrina, which showed that a week before, it was actually very unclear where the hurricane was going to go. In fact, the most likely track was not actually where it ultimately went, which was in this little secondary maximum towards New Orleans, but up the East Coast. And this was a hurricane which was just, I had no idea where it was going to go, could go any direction. Okay, so just looking forward 10 years, I think the development, I mentioned to you, in the early days, I was trying to resist the moves to higher resolution until we had an ensemble system. Now we do. I think the move to high resolution systems is extremely now important for three reasons, at least. One is that these models don't do much better at simulating extremes. An important one, which is sometimes overlooked a bit, which is if you have a high resolution model, you can actually assimilate observations, particularly satellite observations, much better. You can get the information from those observations much better into the model if you have a high resolution model than if you have to rely on parametrizations to do that. And the other thing is that then there'll be no need for some of the key parametrizations, which will reduce systematic errors. The problem is that even by 2030, I think high resolution global modeling especially ensemble modeling, will be a challenge, computational challenge, even when we have exascale and post-exascale. So in my group in Oxford, we're doing quite a lot of work on using artificial intelligence to replace these parametrizations. So we'll get this 50% of compute time maybe down to 10% or even 5% maybe. I won't go into the details here. We've also been looking a lot at reduced precision. Traditionally everything in weather and climate prediction has been done at 64-bit precision. But when you have stochastic parametrization, you start to wonder what on earth you're carrying around 53 or something bits of mantissa or significand. And if you're trying, communicating billions of these variables around the computer, this is really slowing down your time. So trying to get the precision down to the minimum needed is very important. Yeah, so I've been kind of promoting this idea that we can actually indeed make more accurate forecasts if we reduce precision. Now that may seem a strange statement to say you could make more accurate forecasts with reduced precision, but this is exactly what ECMWF have done. And then the next cycle about to be released early next year is an example of this. What they've done is reduce the precision of the models. This is all their models down to 32 bits instead of 64 bits. And they've used the time saved to increase the vertical resolution from 91 to 137 levels. And this is their operational scorecards when they do tests. Just before something goes operational, they test it. And where it's blue, it's basically positive. So it's almost overwhelmingly positive. The point is that this is a free upgrade. The cost of going to this extra vertical resolution has been met by the saving of time in going from double to single. And I just want to say that this is not the end of the story by any means. A postdoc in my group, Matt Chantry, has published a paper, or led the paper, where we've been looking at reducing precision further. And basically, he's found that with the great thing about a spectral model is you can reduce precision as a function of wave number. It doesn't have to be a kind of global thing. And this is wave number going out here. This shows how many mantissa bits you need. And when you're down to wave number 150 or 200, you only need about 5. So a lot of this can be done not only in single precision, but actually in half precision. And a lot of modern computers can now do this mixed precision, double, single, half arithmetic, and this has an enormous potential. We can run hurricanes with half precision and find there's really no difference at all in the performance. And this is an El Nino simulation with a simplified climate model called SPEEDY, which again, we've run at half precision. And the response of the half precision, this is rainfall response to an El Nino event, is almost identical to the double precision version. And the geopotential height response is almost the same. There's one thing which we need to, sorry, I'm coming to the end. There's one thing we need to there's one thing we need to worry a bit about, sorry, not worry about, but take care of, which is that when you go down to 16 bits, there can be issues of systematically rounding to 0, which can lead to systematic errors. And this is a very good example of, if you have 4 bits, you can represent these numbers with different levels of shading. If you truncate it to 1 bit, everything's in black above 55% and everything's in white below 55%. So you lose a lot of information. There's a thing called stochastic rounding. So you round to 1 bit in a stochastic way, and then you retain pretty much the information you had there. So in some sense, noise can be a positive resource. Stochasticity can be as a positive resource. And I think this is a very exciting area for the sort of synergy between software and hardware. If we can implement some of these stochastic roundings in hardware, then we can save a lot of energy, in my view. All right, so whoops. So this is actually my last slide. That I mean, ensemble forecasting has definitely come a long way, which is great, and it's nice to see most centres, if not all centres around the world, use it. But we've got to improve it further, and it's an important part of improving climate resilience, I think. But we've now got to move to these convective permitting models where we can, eliminate some of the key parametrizations like convection and orographic wave drag and this sort of thing. But we have to make much more efficient algorithms to make real use of exascale computing. And I think AI and stochastically rounded low precision will do a great deal. If I had time, which I don't, I would have talked about downscaling and calibration, but these are also going to be vital tools for things like forecast-based finance. And here I think artificial intelligence holds a lot of promise, and arguably more promise than limited area modeling. Anyway, so I think that's probably all I really want to say. The story, as it were, continues, and I hope that many of the people today will be able to contribute in their own way to making, it's essentially about saving lives and making use of science to make people's lives around the world a better than they would otherwise be. Thank you.
Thank you very much for this very interesting account of the story behind the ensemble prediction. And I think this is very encouraging for early career scientists. They should always question the established methods, think outside the box. And I really like the exciting look forward to the inexact computation methods as well. So, I suppose we go forward towards the questions. So the first question I see here is a compliment for your guitars, I think.
Oh.
Someone ringing at the door here. So the next question from Hiem van Straten. You mentioned 50 as the minimum amount of members in an ensemble system. With what reason? Probably it is not smoothness, as we can always dress the discrete distribution that any system produces.
Yeah, I think, there's two issues here. One is extreme weather, when often, there are relatively few members which are predicting extreme weather. So if you're trying to make predictions where the probabilities are, maybe down at 20% or less, you have to, there is a danger of just big statistical sampling errors when you only have 20 or 30 members. And I don't think, I don't think a simple sort of smoothing types of algorithms would necessarily help you in that respect. But I want to say one other thing that, the examples I've shown are just univariate probabilities, and take an example. This is quite a relevant thing for a lot of today's applications where you're talking about renewable energy. How much renewable energy are we going to produce in the coming week? For that, you need to know a probability of both the wind speed being above some value, but also that the sunshine is above a certain, or cloudiness is below a certain value. So it's a kind of a bivariate probability, which involves two completely independent variables of temperature, of sunshine amount and wind. And for these multivariate events, then ensemble size starts to become a really big issue. And you just cannot estimate, for example, bivariate events with small ensemble sizes. It really, it's an obvious statement in a way, because we know that the dimension of the weather system is very large, and the more variables you try to, the more variables that your probabilities are based on, the larger the ensemble size has to be, because it just is matching the fact that the state space is so large.
Mm-hmm. Okay, thank you. So the next question, beyond singular vectors, what are the other ways to define initial perturbations? So
yeah, well, so I didn't really talk about this, but I mean, over the years, what has happened is the 4D VAR system, the data assimilation system at ECMWF, has also been produced in an ensemble mode, if you like. So these days, in fact, I think these days they run 50 perturbed 4D VARs. So with perturbed observations, and they would use the stochastic parametrization within them. So that actually is now an important part of the initial perturbations for the ensemble. However, this is the interesting thing, that the last time, I think this was looked at maybe a few years ago, maybe 3 or 4 years, maybe 3 or 4 years ago, I can't remember the exact number of years, but 4 years ago, let's say, by Simon Lang at ECMWF, that if you take out the singular vectors and only use the ensemble of 4D VARs, you again go back to a very underdispersive ensemble. So, it's an interesting, I think there's some actually quite interesting, probably theoretical stuff to do here to really understand the role of upscale error cascades. But it's clear that with the 4D VAR system, which is being done in a model which doesn't have resolved convection, it has, limited resolution, we're just not capturing, by perturbing observations and putting in the stochastic physics, we still don't have adequate spread in the initial conditions to produce a really well calibrated ensemble. So the singular vectors are still being used, even though they wouldn't have the same weight as they did in the early days, where they pretty much were the only source of perturbations, but they still are non-negligible and can't be set to 0. And I have to confess, I don't fully understand why that is the case, but that is the case.
Okay, thank you. And then the second part of this question is also, what is the optimal ensemble size for medium range weather forecasts? So it's related to this 50 members, I suppose.
Well, the answer is infinity if you if you had the computer time. I mean, the real question is, how do you allocate computer time to this problem? I mean, my view, I tend to resist answering such a question, because my personal view is that this is so important for society that we should always be this type of problem should be centers like ECMWF should have. I mean, we're at exascale now in terms of half precision arithmetic. The Japanese Fugaku computer is pretty much at exascale. So I think an operational center like ECMWF should have completely dedicated exascale computing. The problem is sufficiently important. So if somebody said to me, how should ECMWF partition its resources, between resolution and ensemble size, I wouldn't answer that question. The question I would say is, what would you do if you had an ensemble, if you had an exascale, dedicated exascale system? Then I think, yeah, you could probably run 100 members with maybe 3 kilometers, particularly if you can run the parametrizations with AI and do a lot of the arithmetic at half precision. I think that would be a very and that's sort of what I would see a lot of centers going to by 2030. So 100 members, 3 kilometers resolution, 150 levels.
That sounds good. I'm always surprised at how well it actually already works with only 50 members, given the dimension of the unstable manifold.
Well, yeah, as I say, it's probably because we don't tend to, I mean, at present, most of the products are univariate. I think you'll get hit by the curse of dimension once you start looking at more kind of complex multivariate events.
So a next question by Carlos Pires. The stochastic physics was shown to lead to more accurate spectra, for example, the ENSO spectrum. Does it help to reduce biases in other statistics like extreme quantiles and high-order cumulants measuring non-Gaussianity, like bicovariance, skewness, kurtosis, bispectrum, etc.?
Well, you know, what I tried to suggest was it does help improve the sort of bimodal or multimodal statistics, you know, associated with weather regimes. This is an example of you know, where there's some kind of certainly non-Gaussian multimodality, and it's interesting that well, models tend to struggle, and there's been some papers. I don't know if people know this. There are papers by the Met Office on what is called a signal to noise paradox, mainly in seasonal forecasting, which is that the claim there is if you look at something like the North Atlantic Oscillation on seasonal timescales, ensembles produce too much spread compared with the signal. So their claim is that on these seasonal timescales, the atmosphere is actually more predictable than current ensembles would suggest. And I think the reason, well, a postdoc of mine, Christian Stroman, and myself wrote a paper in the QJ on this a year ago, maybe now, where we claim that this problem is related to the fact that the weather regimes in models are typically, if you think of a weather regime as a potential well, then the potential wells are too shallow in the models. And so the ensembles, you know, if you think of ensembles as ball bearings in a potential well, then the ball bearings are just too spread out because the potential well is too shallow. And we think that's the reason why on these seasonal timescales, the spread is too large. And stochastic physics, but this is a very beautiful example of how non-linearity can work in a completely counterintuitive way, because you would say, oh, well, if you added stochastic physics, that would increase the spread of the ensemble. But actually, it can do the opposite. By actually stabilizing these regimes, it confines the ball bearings to a tighter region of state space. And so the ensemble spread actually decreases. So there's a beautiful, beautiful example of non-linearity. I think, by the way, I should say, I think in this particular case, the stochastic physics is a kind of a surrogate for resolution, and probably the full resolution, explaining this, or at least solving this problem will actually not be completely solved by stochastic physics, but will probably require higher resolution as well.
Mm-hmm. Okay. So, question by Stefan van Utsem. A very interesting presentation, Tim. Concerning your last comment, why do you see AI as providing more promises than limited area modeling to get small scale information?
Oh, Stefan, you asked me a question I could talk for. Leslie, just before I just embark on this, what time are we planning to sort of finish?
Yes, it's already 3:38. Sorry, I forgot to turn on my camera. So yeah, maybe I can just finish the questions that are still in the Q&A. Maybe we can go on for about 10 minutes if that's fine.
All right, well, let me just answer that one because it's a really important question. And I actually think this needs a lot of discussion in Europe and internationally. But I'm thinking here perhaps more about the problem in developing countries, getting forecasts out, you know, so that the Red Cross, Red Crescent forecast-based finance system can work. You know, what we want is highly, you know, regional postcode scale forecasts, not just, you know, 2 days into the future, but 10 days into the future. If they're going to be reliable, you know, they've got to be done in an ensemble mode. There's got to be a lot of hindcast data so that, you know, we can validate if the forecasts really are being used, you know, for either providing finance aid or or providing emergency relief. The people have got to know that these local regional forecasts are reliable. The problem with limited area models is that most MET centers just don't have the resources. They don't have the resources to run ensembles of limited area models. They don't have the resources to run these ensembles out to 10 days or 2 weeks. They don't have the resources to run big hindcast data sets to validate and calibrate the ensembles. So it's completely unsatisfactory. I mean, there may be some European member states that can do it, but by and large, most countries of the world can't. And I think ideas in convolutional neural nets or these generative adversarial networks seem to be providing enormously skillful capabilities to downscale, for example, to downscale reanalyses to the subgrid regional scale using information of topography and whether the flow is convectively unstable or just large scale unstable. And I think this is something that regional net services can develop in ways which they just don't have the resources to do with limited area models. So I fear that limited area modeling is actually in many places holding back our science, and certainly holding back the application of our science for good decision making. But this is something which I think we need a dialogue about, and it's an important area actually.
Okay, thank you. I'll go to the next question by Nick Watkins, if you still have time, of course. Do you think Chuck Leith's view of ensembles was partially conditioned by his interest in Langevin models?
I looked up a little bit, possibly is the answer. I looked this up actually because it's quite interesting. I can get a bit diverted with these questions. Chuck Leith started life off working with people like von Neumann and Stanislav Ulam on the hydrogen bomb. And the whole Monte Carlo method actually developed out of developing hydrogen bomb code, because they wanted ways, when you have neutrons diffusing around in some plasma, the neutron equation is essentially probabilistic. But then they realized how, it's impossible to solve it. So they said, well, let's just treat each neutron as a little point particle and just do multiple integrations with the neutrons diffusing in different ways. But there, all they were interested in was an expectation value. They wanted the average effect of these diffusing neutrons. So the natural thing was not really to look at higher order moments or anything, but just to look at the mean. So Chuck Leith left the field, I don't know when it was, in the early 50s maybe, or sometime, and then started working on climate models and wrote this paper on Monte Carlo forecasting, really just bringing his probably expertise from this earlier work into weather and climate. But he didn't really, in my view, emphasize enough the importance of at least the dispersion of the ensemble, and most of the work. And as I say, the headline message in the abstract, and people still quote this is the reason I'm slightly frustrated about this, is people still quote this at me today. They say, oh, didn't Leith show you only need 10 members? Why are you using 50? And that's the reason why he focused entirely on the ensemble average. And that might be fine for calculating the mean effect of neutrons in the plasma, but it's not what you want for forecasting extreme weather in society.
No, especially if you put the output of your model in another nonlinear model.
Yes, that's right. That's another way of, by the way, yes, you're quite right. That's another way of looking at it. You could say, well, the final, what you're actually providing society is not actually the weather. It's, should you evacuate, or should you move your livestock? And for that, you feed all the ensemble members into a hydrological model, and then that into a decision model. So ultimately, it's like in quantum mechanics. You ultimately do collapse the wave function down into if you like, a deterministic yes or no state. But collapsing it down at the meteorological level is much too early in the process, and you lose all the information, the relevant information, if you do that.
Great. A question by Stefano Tibaldi. Is it possible to combine singular vectors with ensemble 4D var, or Ensemble-Kalman filter techniques?
Stefano Tibaldi. No, that rings a bell. Stefano, how are you? That's great. Stefano was somebody who attracted me to ECMWF in those early 1980s. I would not be there and I would not have had the career I have had without Stefano and his encouragement. And Stefano and I worked on some of these early, more statistical schemes to try to forecast the forecast skill, which were interesting, I think, scientifically, but were not ultimately the way forward. Yeah, can singular vectors be used in 4D VAR? Oh, well, this kind of, yeah, this rate, I mean, there was an attempt to do that I forget now when, in the 1990s probably at ECMWF, where going to more technical information than you might want, but where the covariance matrix in ECMWF, the covariance matrix in 4D VAR was cycled from one assimilation time to the next in what was called a reduced rank form by projecting onto singular vectors. You project the covariance matrix onto the singular vectors of the day, and you kind of propagate that reduced rank form into the next analysis cycle. The problem is this non-modality. It didn't really work, and the reason I think is that the non-modality of the singular vectors kind of kills you almost. So in other words, you have this covariance matrix projected onto singular vectors at the end of one analysis cycle, and then you want to project that onto the initial singular vectors of the next analysis cycle. But because they are so separated in spectral space, the projection all ends up being virtually zero. So you don't carry any useful information through. So that method never worked. So I don't know, the answer I suppose is we still don't know, but techniques that have been tried as yet haven't been successful. But that's a good question. Mm-hmm. Anyway, it's nice to hear from Stefano.
Thank you. So next question by Susanna Corti. Do you think that it could be possible one day to build up ensembles which size is kind of flow dependent, so dependent on where you are in the attractor?
Oh, hello to Susanna as well. Nice to, yeah. You know, one of the problems in operational forecasting is always, you know, you have to worry about getting stuff out in a useful time. So there's this very tight window of opportunity for making a forecast, and if you decided you needed more, more ensemble members, that's the problem, I suppose, that you might decide today that you need more ensemble members, but then you've got to have enough, you've got to make sure then you have enough computer time available to run that, that worst case scenario for ensemble size. So I don't know. I mean, that's all I'm saying is the question, in principle, yes, but I think the question is complicated by the sort of delivery schedule for an operational forecast. If it comes, if it comes an hour late because you run an extra 50 members, it may not be, those extra 50 members may not be then as useful as you might have hoped them to be. So I'm just saying that's an issue that you have to think about.
Mm-hmm. Okay, great. There are still some more questions, but I suggest maybe we conclude now. Maybe we stop the recording, and unless you feel